going to talk about inductors and capacitors. Inductor. An inductor is an electronic component consisting of a coil of wire with an electric current running through it, creating a magnetic field. The unit for inductance is Henry. 1 Henry is the amount of inductance that is required to induce 1 volt of electromotive force when the current is changing at 1 ampere per second. One important application of inductors in active circuits is that they tend to block high frequency signals while letting lower frequency oscillation pass. Note that this is the opposite function of capacitor. Combining the two components in a circuit can selectively filter or generate oscillation of almost any desired frequency. Several parameters that are important while selecting an inductor. First one is Q factor. Q factor or quality factors refers to the ratio of an inductor's reactance to effective resistance. This value of frequency dependent Q factor impacts the shortness of the center frequency in an LC circuit. Usually a high value of Q factor is preferred. Second one is self-resonant frequency, which describes the frequency at which an inductor stops working as an inductor. For RF circuits, self-resonant frequency should be chosen such that it exceeds the operating frequency of the circuit. As the inductance is 0 at the self-resonant frequency, Q factor is 0. Third one is saturation current. Saturation current refers to the DC current which causes the inductance to drop by a specified value. The inductance drops because the core can only store a certain amount of magnetic flux density. While saturation current is related to the magnetic properties of the inductor, rated current is related to physical properties and it describes the maximum DC current that can be passed in an inductor. Fourth one is DC resistance. DC resistance refers to the resistance inherent in the metal conductor of the inductor and it can be modeled as a resistor in series with the inductor. DC resistance is an important parameter in DC to DC converters designed as the resistance leads to losses, thus reducing the efficiency. Tolerance. Tolerance is the variation in the inductance value of an actual inductor compared to the specified value in the datasheet. This could result in unwanted shift in frequency selection of an RF filter. Next one is electromagnetic interaction or electricity to magnetism. The right hand side diagram shows that the magnetic field flux is generated in the space around a current flowing through a piece of conductor, and the left hand diagram shows the magnetic field around a coil is the superposition of the magnetic flux generated by each section of the coil. Electromagnetic interaction or magneticity to electricity. Electric current is induced in a conductor when there is changing magnetic flux in the surrounding space. The diagram shows that the direction of current is always opposite to the direction of motion. Self and mutual induction. A time-varying electric current in a coil will cause a time-varying magnetic field in the surrounding space, which in turn will induce electric voltage and then current in the same coil or a different coil in the neighborhood. Inductance. Inductance is determined by the parameters of the inductor. L is equal to N square mu A by L. Mu can be written as mu R and mu naught. L where L is equal to inductance of coil which is in Henrys. N is equal to number of turns in wire coil. Mu is equal to permeability of core material. Mu R is equal to relative permeability. Mu naught value is 1.26 into 10 to the power of minus 6. A is equal to area of coil in square meters. L is equal to average length of coil. When a medium of high permeability such as an iron core is inserted into the coil, its inductance L is increased. Application of inductors. Tuning circuits, sensors, storage energy in a device, induction motors, transformers, filters, shocks, ferrite belts, inductors used as relays. These are the application of inductors. And the types of inductors. There are several types of inductors. I am going to discuss some thing. Molded inductor, yard wound inductor, iron powder toroidal inductor, ferrite core toroidal transformer, adjusted yard wound inductor, variable inductor. Next topic I am going to talk about is capacitor. A capacitor is an electrical circuit, behaves as a charge storage device. It holds the electric charge when we apply a voltage across it, and it gives up the stored charge to the circuit as when required. The most basic construction of a capacitor consists of two parallel conductors separated by a dielectric material. When we connect a voltage source across the capacitor, the conductor attached to the positive terminal source becomes positive, and the conductor connected to the negative terminal of the source becomes negatively charged. This point is the right hand diagram shows this. Because of the presence of dielectric in between the conductors, ideally no charge can migrate from one plate to another. So there will be a difference in charging level between these two conductors. Therefore, an electric potential difference appears across the plates. The charge accumulation in the capacitor plates is not instantaneous, rather it is gradually changing. The voltage appears across the capacitor exponentially rises until it becomes equal to that of the connected voltage source. The potential difference or voltage between the plates is proportional to the difference in the amount of charge on the plates. Q is equal to Cv, where Q equal to charge, V equal to voltage, C equal to capacitance. Capacitance. The capacitance depends upon three physical parameters, and these are the active area of the conductor, and the distance between the conductor, and the permittivity of the dielectric medium. C is equal to epsilon A by D. C, where C equal to capacitance in farads, epsilon equal to permittivity of dielectric, A equal to area of plate, overlap in square meter, D equal to distance between the plates. Selecting a capacitor based on tolerance, it must be checked if the working of the circuit depends on precision capacitance. If it requires narrow capacitance, capacitor with the lowest tolerance should be used. The capacitance of a capacitor will never vary beyond its rated tolerance unless it gets damaged due to excessive voltage or environmental conditions. Second one is operating temperature range and temperature coefficient. If the circuit is temperature sensitive, or capacitance should not vary beyond a limit over a range of temperature, its operating temperature range and temperature coefficient must be taken into account. Based on the temperature coefficient and temperature curve, the extent of change in capacitance should be calculated. The temperature sensitivity of a circuit can also be dealt with by using capacitor of positive and negative temperature coefficients together. In that case too, the maximum variation of capacitance over a range of temperature must be calculated. Third one is frequency dependence. Many capacitors have their capacitance dependent on the frequency and may not be suitable for a specific range of frequencies. Depending upon the circuit, the frequency dependence of the capacitance should be essentially considered. Fourth one is operating losses. Operating losses can be an important factor where circuits need to be energy efficient, like battery operated circuits. For such circuits, careful selection of capacitors should be made considering their dissipation factor, dielectric absorption, leakage current or insulation resistance, and self-inductance. All these losses must be minimized to improve efficiency and battery life of circuit. Fifth one is ripple current and pulse voltages. These are quite important checks. The circuit must be manipulated for the possibility of pulsating voltages and maximum ripple current. A capacitor of appropriate ripple current and working voltage rating should then be chosen. Sixth one is polarity and reverse voltage. If an electrolyte capacitor is used in a circuit, it must be connected in the correct direction. Its reverse voltage rating should be at least twice the possible reverse voltage in that branch of the circuit. Next, power. Power factor correction, sensor, power conditioning, coupling, tuning, pulsed power and weapons, timing elements, signal processing, smoothing. These are the application of capacitor. Types of capacitors are listed below. Aluminum electrolytic capacitor, mount electrolytic capacitor, wired-ended electrolytic capacitor, surface mount electrolytic capacitor, motor run capacitor, suppressor capacitor, three-terminal capacitor, solid-state tantalum capacitor, surface mount ceramic capacitor, radial ceramic capacitor, polyester capacitor, polypropylene capacitor, memory backup capacitor, trimmer capacitor, polystyrene capacitor. Difference between inductor and capacitor. Capacitor, inductor. Capacitor, it resists changes in voltage. Inductor, it resists changes in current. The voltage in the capacitor does not change instantly. The current in an inductor does not change instantly. Unit of capacitance is farad. Unit of inductance is Henry. Voltage lags current by pi by 2. Current lags voltage by pi by 2. Energy is stored in the electric field. Energy is stored in the magnetic field.